All right, welcome back. We are game 3001 in the winter 2021 semester, and it is week 10, although it says lesson 9. This is what this is. And we talked about behavior trees today, but what we're doing in lab is we're going to follow up with decision trees. We're going to actually code a decision tree. Last week we did line of sight, and we haven't been able to do radius yet, but radius should be fairly straightforward. Also, distance to target. And when we talked about this morning, in this morning session, is this idea of this kind of tree. So I want to kind of code this tree, not this other crazy one, all right, that we were looking at. So I want to look at this tree. And really what I want to do is think about how to code this in straight order. One of the things we need, though, is the ability for us to set decisions or, set conditions for the line of sight and for radius and if we're close enough to fight, kind of thing. So those are the things we need to set somehow in the tree structure. And which means, if I think about this clearly, that I need to somehow convert my ship to an agent, to create some kind of AI agent. And the agent itself may have different components. One of the components might be the AI brain, which is in the form of a decision tree. Okay. So this is the way I'm thinking about it. You may implement this differently. It's totally up to you. Okay, so one thing at a time. First of all, let's convert our ship to an agent. All right, what does that mean? Well, first I'm working with a starter. Here's our Lab 7 starter, and in Lab 7 starter is actually just Lab 6B, which is what normally we do. And I've created Lab 7B as a final. There's nothing in there right now. It's just Lab 6B copied. Okay, across. One thing we want to do with Lab 7B is kind of convert this part. So we can say that this will be Lab 7, right? This part here. And I'm just going to commit changes. That's online, and I got to pull it down on GitHub. So I'll say git pull. All I've done is I've downloaded Lab 6B, and I've created Lab 7B locally, which is looking like this. Here is Lab 7B. All right, so cool. I've got this thing. Let's run it, and let's get going on this thing. So we have a lot of work to do, and 2 hours is not enough time for what we have to do, because I'm really pushing myself to get all this stuff done so we get ready to do more next week. And hopefully it'll help you with your assignment 3 and 4, which is what I want to try and help with. All right, so let's run this thing, and we always try and run the thing that we used to have before, compared to what we had today. Make sure that it still runs. Always check to see if it runs. Yay, GeForce Game Ready driver is available. We're not going to download that right now. No, I refuse. And yes, I have an RTX 3070, but no, I'm not going to update it today. All right. Cool. So this is what we had last time. We had some very simple scenes. I'm not even updating it. I know that Alex told me there was a bit of a bug. I'm not even updating the bug. Literally, I'm just going to go from here. And we don't care about line of sight today. Anyway, we care about, I demonstrated the idea of line of sight, and hopefully you can take it further for your stuff. Ethan, yes, it's always on GitHub. So on GitHub, if you look on Blackboard, you can see that on Blackboard, I have both a starter where I want you to start from and a final where I'm doing it right now with GitHub. So that's where it is. Same thing every week. Okay, so I have this, and I want to be organized. So let's make a new section. So I'm going to say, so on the template, I'm going to right click, and I want to add a new filter. And let's call this decision. Right, so we know that this is our work. This is where it's going to be in here. So we don't have to run around and look at stuff. I know that in my game objects, I want to convert my ship to an agent here, because there's a lot of stuff in here that is not game object related. It's specifically related to AI, right? So let's grab my ship and drag and drop it into decision for now. Okay. Decision is going to be broken down into a couple of new filters. Let's make a couple filters here. One of them is going to be a filter that is for actions. We're also going to make a filter, right, for conditions. And then we're going to make another filter for agents. Right now we only have one agent, and that's going to be the ship. but we're going to take this ship and put it inside agents. I want to make the agent, and right now I'm going to use the ship as a blueprint for the agent. All right, that's what I want to do. So I want to make a brand new item. My new item is going to be a .h. I'm going to call this agent.h, and it's got to go in the right spot. Can't be in template. It's got to go inside of src folder, which is the source folder. Select, okay, agent.h, and click add. There's agent.h, and I'm also going to make another one right away, and I'm going to call this one the CPP, and this is going to be agent.cpp, and add that in there as well. And I'm going to include the agent.h. Okay. So that is what I want. So now what I want to do is I want to grab my ship.h, and let's pull it aside. So I'm going to double click it, and then in my ship.h, I'm going to pull it into this split screen thing. What I'm going to do here, so I have a side by side, and what I want to do is pull stuff into my agents.h that I need. And let's just do some of this. So copy pasting is going to help me go a little faster. So hopefully, so this is going to be called agent. Okay, so agent, and I also want to do if not define agent, right? Then def agent is what I want to do, define it, and end if, and if, and I want to say that we defined agent. Okay, and all the work is going to be in here, where I'm going to grab basically the entire class, not including this stuff right now. Well, maybe I'll include vec4. I'll grab that too. But I'm going to grab all this and all the way to the bottom, copy and paste it in here, which is going to help me code up the stuff that I need. So it's not going to be ship. It's going to be agent. I need a display object because I need to be able to modify that, because agent is going to be a specialized display object. I'm not going to make it ship. It's going to be called agent, right? I need the draw, update, and clean functions. I don't need turn right, turn left, move back and forward. I don't need any of this stuff or move. That is going to be specific to the ship, so we can get rid of that. My target position, get current position, max speed I don't need, but the other ones I need. Get line of sight, has line of sight, get current heading I need. Set target position, set current direction, set max speed I don't need. Set line of sight distance, has line of sight, and set current heading. All this stuff I need, right? So this is the majority of what the ship had, right? And I'm going to get rid of it over here eventually. I don't need check bounds or reset. We can get rid of that because that is ship specific. I don't need max speed, that ship specific, and turn rates. I don't need any of that stuff. Change direction I will need, right? Current heading, current direction, target position, line of sight distance, has line of sight, and line of sight color I need. And I'm also going to need set line of sight color and has or get line of sight color, which I don't have. So let's get those in there. So and let's make sure we bunch the getters and the setters together. So this will be a void. So line of sight color is a GLM vec4, which is get line of sight color. We're going to need to get that. And we're also going to have to set line of sight color kind of at the bottom. So again, void set line of sight color just to get that going, which is a new GLM vec4, which is going to be color. Okay, there's that stuff that we have here. Also, you know what? Let's make sure that this is not new position, it's new underscore position. And this is going to be new underscore direction, which is what it should be. Okay, which is going to mess up some of our stuff, but it's okay. Fix it. So this, my friends, is the .h or agent.h. Are you with me? Check mark if you're with me, X if you're really far away and you don't know what the heck I did right now. But this should be pretty much in line with what you've seen before. So I'm making a brand new class, agent, and agent is going to be the superclass for AI agents going forward, right? Why? Because so far we've been kind of adding pieces to the ship to make it go. And I want to make it so that the ship is an agent, and I can choose to make a ship an agent as opposed to just a display object. All right, so next part. I need to implement all this stuff on the CDP file. So let's do that. So I'm going to go to agent. And I'm going to say generate definitions by declarations. It's going to install all this stuff, but I don't need for my agent draw, update, or clean. So let's make sure we set these things because these are pass-throughs, right? So I don't want draw, update, and clean because draw, update, and clean are going to be handled by the actual ship itself. I want them to have specific details. The rest is things that I'm going to use, but I want draw, update, and clean to be ship specific. Okay. So let's do that again. So I'm going to go here and I'm going to go to the hammer and I'm going to say generate definitions by declarations. And I don't need draw, update, and clean. So get rid of those. Agent and agent is okay. I'll fix those in a second, but the rest we're good to go. Let's finish and set those up. So there's those. We can make our agent destructor a default destructor like we've seen before in the past. And now, sure enough, we're going to copy and paste some stuff from the ship.cpp, which I'm going to pull over here. There we go, into the ship.agent.h. And also, we got to see some of this stuff, get current heading, and all this stuff is going to be set on the ship side. But on the agent side, anything else that has to be set up is going to be done in the constructor. We'll see. I'm not changing any of this stuff right now. I'm going to go through and just modify the things that I need, like get target position. So scrolling down, get target position. I'm just going to copy paste just to make it easy because it's the same structure. Get current direction, right? Making sure that that's good. Max speed I don't need. Return line of sight. Yes, this is line of sight distance. I want that. And has line of sight. Let's grab this and put that in there. And get current heading. Again, I'm just copy pasting from here into there. And get line of sight color. That's new. So that's going to return m_line of sight color. Also set target position. Now the setters. So set target position, that's this. And we know that I've changed the set target position thing to this. My variable name has changed, that's okay. And same thing with set current direction. So set current direction is right here. So grab that and put that there and change the variable name to this. All right, so that is something that I've changed. For those people just coming in, just bear with me while I go through these small changes and then we go through it. Set line of sight distance, that is something that I put in here, up here. So set line of sight distance. So these are getters. And here's the setter for this, set line of sight distance. And set has line of sight, that's right here. Now this is interesting. I also set the color right here to whatever the color is. So this is what that's going to happen. Wherever the color is, I'm going to set the color to red or green, depending on what's going on there. Okay, and set current heading, I need that part. That's this part. And I'm also going to set current direction when I set the current heading. So copy that, set current heading, set current direction. Set current direction does our calculations. Set line of sight color, that's going to say that m_line of sight color is going to equal to the color value that I'm passing in here. And then finally change direction, which is a key function that's private, right, is this function down in here, which I'm going to grab all these three things, except I don't need the ship. I don't need to draw the ship again. I'm going to grab this and basically do this, okay? One thing I don't have is util, which I'm going to include in my library really quickly. And we know that this is not required because this was just me trying to show you that getting texture size for a ship that's turned, it's not going to make any difference. All right, so that is everything that I grabbed from the ship to make it work on this side. Let's use Resharp or C++ to fix things up. So we know that this should be const, and so should this, and so should this, and this. All those, heading, as well as color. So those are all const, And that is my new agent, agent.h and agent.cpp. I'm going to save both of those. Nice, nice. And what I want is for me to, after I've saved all this stuff, to make sure that the ship uses agent. So ship.h is now going to inherit from agent. So all I'm doing is made agent with all this stuff. Let's remove things that we don't need from this side from that I put over here. So again, this will be using agent, right? Agent is a new class, which is going to be a display object. So we can get rid of this, right? I made them. Agent.h and CPP, I made them. I don't need them to be final. Let's not make that final. So ship.h is going to inherit from agent. And all I've done is I've taken elements out of ship and put it into agent. Let's remove things now from the ship that I don't need and that I already have an agent. Final means you can't inherit from it. Just a second, Miguel, and I'll put it up on GitHub for you. One sec. So I don't need get target position, get current direction. That is agent specific. I don't need get line of sight distance, has line of sight distance, get current heading. That is agent specific. I don't need set target position, set current direction. That is agent specific. And I don't need set line of sight, has line of sight, and current direction or current heading. That is agent specific. So those are gone. Maximum speed and turn rate are okay, but I don't need change direction, current heading, all this kind of stuff. That's all agent specific. That's what the agent's going to do for us. All right, so that is what the ship looks like. I've just basically removed a lot of it. Texture manager is okay. GLM Vec4, HPP, I'm going to keep for now, but I probably don't need it. But it is now, the ship is now starting to become an agent. So it's a specialized form of display object. All I've done is move stuff from here to there, because maybe in the future I'll have other agents other than just the ship that allow me to do a lot of other stuff. Okay, let's go into the ship.cpp really quickly and fix all these crazy errors. Well, it looks like a lot of errors, but actually it's not. Get current heading or current heading setting to 0 is just me using the set current heading. So set current heading to 0.0f. That's just using the setter now from the agent, all right? So I don't need this. And then current direction is equal to GLM Vec4 or Vec2. I can set the current direction, set current direction. I'm just keeping one for one. I probably don't even need all this stuff anymore, but hey, let's just keep it so that it works. And then we can change this and we can just use this. So that is get current direction. I'm just using the setters. Turn rate, I'm not going to change because turn rate is specific to the ship, okay? Line of sight distance though is, so set line of sight distance, that's going to be equal to 400.0f. Okay, so that is specific to what we're doing there. Okay, and finally, line of sight color, I'm going to set that to set line of sight color to whatever the color is that I'm going to set right here. This is where I need line, the Vec4s. Okay, and that gets rid of that. So my constructor is fixed. There was a lot of errors in my constructor based on the things that I didn't need from my the stuff that was agent specific. Let's go down the pipe here and look for other things. One thing I can do now is break the split. This is annoying now. So I can get rid of .h and pull CPP over here so we can see it in full screen. So let's keep going with the ship. I'm just going to get remove all this stuff, and then I'll put this up on GitHub and you can compare my code with your code. All right, so current heading is get current heading. This one, right? And get line of sight distance, get line of sight distance, and get line of sight color, get line of sight color. I guess I'm just doing one to one. Okay, I'm not trying to revamp code. I'm just doing, you know, kind of converting. This is a little bit more tricky. This is set current heading, and I want to set current heading to the current heading, and then plus the turn rate, m_turn rate, just to keep it the same. I mean, we're not really using this turn right, turn left function right now, but let's make it so that you understand how to do it. And then we're comparing get current heading. If it's greater than 360, then we want to set current heading. let's make sure that this is a semicolon here. We want to set current heading here, set current heading to the get current heading, right, minus the 360 degrees. So this is the way we did the turning the last time. And then what we can do is change direction. We don't need to change direction because when I set current heading, if you look at that, go to definition on the here, set current heading actually changed direction too. So we don't need that anymore. And we used to do that twice. So we don't need this. So this is kind of a slimmed down version of turn right. Turn left and turn right are almost identical, but what we're going to do is we're going to just drag this in here, and we're going to change this to a minus and get rid of this. And same thing with current heading. This is almost the same, but it's going the other way, and that's okay. And this part is almost the same, except it's plus, not minus. So this is plus here, not minus. And let's get rid of this because we don't need it. Okay, so that is your turn left and turn right fixed with the new settings from agent. Okay. Move forward again is get current direction, current direction multiplied by speed. Same thing with move back. So move forward, move back, get current direction, minus speed. Move is fine. Okay, now here's agent-specific stuff we can get rid of. So I don't need this stuff anymore because that is all part of my agent. Get max speed I do need. Float distance, current heading, all same lines have gone, right? And same thing with all this stuff. So all these are gone, right? And same thing with this. So these are what's left. All I'm doing is removing, guys. Don't panic. I'm removing stuff from my ship that I already have on my agent. And the last thing is that funky little method, change direction, which does some calculation when I take my cosine of the current heading multiplied by deg to rad, and I convert it and I get your normalized current heading position. So I don't need this anymore because it's all included in agent. Okay, so that is my ship, right? And all I've done is I've removed stuff that I don't need that I put in agent. Let's check it. I'm just going to close all these things off. And I'm just going to run this thing right now and see what happens. And I'll put this up on GitHub. Now, I went fast, and I really do apologize. But I had to do this because that is kind of a requirement for everything else that goes forward. I could have given you this file, right? But really what we want to think about is that everything works the same way that it was working before. So if I want to move my ship, then it should still move, right? If I move my target, I can still qualify. It doesn't uncheck the line of sight. That was the error that Alex picked up last time. But again, this is the ship moving around. I can move this. I can move my ship around. This kind of stuff up and down, no problem. But one thing that I can't do is it doesn't do line of sight, but it doesn't matter. Okay, so we can fix that problem later. So this is where, under the Solution Explorer, I'm going to put this up on GitHub. Okay, so for people who just came in and you're late, whatever, doesn't matter. Here it is. I'm going to say that I converted ship to agent. That's what I did. Commit all, right? I'm going to go home, and I'm going to go sync, and I'm going to go push. So that is in the final version. You can see all the changes that I made in about another second. There we go. If you look up online now, under the Lab 7 structure right here, you can see that I modified my ship to agent. If you go in here, it'll show you the changes that I made, in the SRC folder, right? So here's the SRC folder, the changes that I made to, just to catch up to the ship, right? So if you look down, as an example, here's ship.cpp and ship.h down here. You can see that those are the places I made changes, as well as I added agent.h and agent.cpp. They're up here, and agent.h, you'll have all of its glory. Copy paste this stuff, guys, into your project so you're in line and up to date with me, so that way you're ready to go. All right, so that should do it. And I'll wait for you guys. We've done this part, so let's cross this part out. So why do we need to do that? Because I can't just say the ship is a display object. Display objects don't have line of sight. Display objects don't have a lot of stuff, but an agent now does. And because we have an agent, when we build a decision tree structure later, we can say, hey, I need a reference to an agent that has all this stuff, so I can get information from the agent to pump into the decision tree. Otherwise, decision tree is not going to work. It's going to be way more difficult to do, right? So that's why I made all those changes. So make sure you convert your ship to an agent. Otherwise, it's going to be way more difficult to do what we're going to do. All right. Hopefully that was explanatory enough. Miguel, are you good? Because I know you said, like, where'd you get that stuff? In which folder? Well, now you know where it is. Are you good, Miguel? Neil's good. I see. And everyone else good? How are we doing before we move on? I got Eric's okay. And Neil and Eric, looks like. Everyone else not answering, but that's okay. Oh, Jacob. I see Jacob put a check mark. And that's it. Okay. And Miguel says, good to continue in the chat. Very good. Thank you for that feedback. Okay, so now, what do we do now? What's next? So we need to do the next part, which is build a node, right? A node class. And there's different kinds of node classes we can build. All right. Again, I'm going to work inside of this decision filter right here. And that is an important place to work, because I think when we look at the tree node that we're going to create here, I'm going to make two pieces, treenode.h and treenode.cpp. Let's make new items. So new item, I'm going to go to the .h area, and we're going to call this treenode.h. It's going to go in the src folder, add. I'm also going to immediately add a new item, which is the treenode.cpp. So let's do that. So treenode.cpp. Let's add that in and make a reference immediately to treenode.h. Okay, so that way you have that working. What we want in here is what a tree node is. Again, it's if not defined tree node, then we want to define tree node and end if. Okay, so this, what this does is it creates our guard. Okay. And what we want is, tree node is really a struct, right? We want it to be available to us in public format. It's going to have some issues, but that's okay. I need it to have a constructor that is default, and it has to be virtual, a virtual destructor, because we're going to inherit from it, right? So we're going to say tree node is going to be equal to default. And I also want to make it so that the constructor is virtual. So the destructor is going to be virtual destructor. Okay. And that's also going to be equal to default. If I can spell default properly, but that's okay. We can just copy paste on that one to fix the problem. So I want to make a default virtual destructor. When I make a virtual destructor, this becomes something that I'm going to inherit from. That is not something that I can build, an abstract object or interface. I want to make it so that I have the name for the tree. Every node can have a name. I can also use an ID if I really want to. And I'm also going to store a bit of data in terms of Boolean data. So I'm going to say that by default, the data that I'm going to store in my tree node, if for every node, is false, right? And this is a way I can get around taking care of conditions and that kind of stuff. I can set the condition to this if I need to and carry forward some data. Data can be anything else you want. You can carry it as an object. And we can make a further abstraction, which the data object can have two pieces. It can have a Boolean, and even it can have a function reference, a callback function if you want, for what's going to run when you get to this node. Okay, so but for now, we're going to leave it at this, and next week maybe we'll add to it. All right, and then now we need a couple of things. So we need a tree node pointer, which is going to look at the left node. We're going to set that to null pointer. Excuse me. And we need a tree point noder for the right node pointer, which is going to be also a null pointer, pointer. Okay, and then we need, I might as well, I probably don't need it right now, but I'm going to put in the parent node as well, and I'm going to leave that as null pointer. And we don't need it for today, but maybe for behavior trees, I may be able to use a tree node that is very common to both behavior trees and decision trees for next week if I do it. So bool, I'm also going to see if it's a leaf which it's not going to be a leaf by default. That's my decision tree, my tree node. Okay. And that is kind of our building block. We're going to build from there because we're going to make different kinds of nodes. I'm going to make a condition node, an action node, those two nodes. These are things that I'm not going to inherit from. Okay, these are things that I'm going to use as a foundation for everything else I make. So let's add a couple more. I'm going to add in a new item, and we're going to call this one. This is also going to be an interface. All right, so this is going to be an interface. So we're going to call this the condition node. The condition node is like a tree node, but it's got a specific additional property to it. I'm just going to grab everything from tree node here just to start me off. I'm going to grab all this part, so just to copy paste so I don't have to kind of do all that from scratch, and we'll modify it. And the same thing goes with this part, because we're in a rush today. Not like we're not in a rush any other day, but today specifically we're in a rush. So this is going to be the, again, did I mess up? I did mess up. Hold on a second. Treenode.cpp. Did I even need a treenode.cpp? I don't think I do. Hold on a second. Let's get rid of my treenode.cpp. I don't need that. Treenode.cpp does not have to exist. Remove. Okay. But one thing, when I do this, by the way, if you ever remove something like that, if I go to my find in Explorer, and if you go through, guys, do the cleanup, right? Tree node, that just deleted it, but it didn't kill the .cpp. Let's get rid of that just in case if there's other side effects. We just did that on the file explorer here. Because I don't need it. Tree node is really just a struct. I want my condition node is what I wanted, right? So sorry, I made a mistake there. So grab these things here, go here and call these condition nodes. So much for saving time. Condition node, right? And same thing with this. I'm also going to do the same thing with the bottom part, which is right here, just so that way we have that stuff out first. And so what is a condition node? A condition node is a tree node, but that has some kind of condition. It's going to definitely be an interface. So the difference between a tree node and tree node, extra C's, tree node.h. The difference between a tree node and a condition node, so it's going to be a class this way. So this is going to be a condition node. A condition node is going to be a public tree node type. And we're going to make it public for now. But the one thing that's going to be different is the condition node is going to have a constructor. And what I want is in the constructor function, I want to say that isLeaf by default is false. Why is that? Because if it's a condition, remember, let's take a look at the condition. If I looked at the diagram, conditions here can't be leaves, right? It's going to be passed through. Conditions are only the bottom are leaves, and those are actions. So actions are leaves, conditions are not. All right, so that's why I say condition node. When you instantiate one, condition node is not, and I want to make it so that it's a virtual destructor, right? Which is also going to be default. All right, so that is my virtual destructor, and the only thing I want is a pass-through, because this is an interface, of a Boolean condition that it's going to be set to 0 for now. So this is something that I'm going to replace. Whenever I set these to virtual and then equals to 0, this is a pure virtual, which makes this class abstract, or it could even be considered an interface. If you're working with C# or Java, this is like an interface. I'm creating some stuff that needs to be overridden if I inherit from it. So if I inherit from condition node, then I need to override the condition statement or the condition method, okay? Similar to condition, I'm going to make action. So I'm going to copy this part here and save it. And let's make a brand new one called action. So I'm going to say add a new item. I'm going to make a new item called the action node. So action node .h. And I'm going to copy and paste in there. So instead of condition node, this is going to be called action node, right? action node, the difference between action and condition, right? It's still a tree node, right? But it's an action node, different type or different interface, right? And is leaf is true. That definitely is true. So all actions are leaves because they're the bottom of the tree, right? And instead of a condition, instead of all actions having a condition, the action has an action that it's going to execute. Okay, but notice it says that the action will execute and give me a Boolean. I don't care about Boolean actions; it can be just void. So the action is going to execute, and I don't care how it executes. And then this part here is going to be something that I put in here. Right, so there it is. That is my action and condition. Let's put this up on GitHub. So Team Explorer, I'm going to go to Home. I'm going to go to Changes. I'm going to say that added action and condition nodes. So these are just like building blocks, okay? They're not the final versions, okay? And why am I doing this? Because I want to accomplish the goal of putting together different kinds of nodes in my tree. So tree node is the base. This is the base node, right? And then I'm adding different kinds of tree nodes. One of them is going to be a condition node, and the other one is going to be an action node, okay? Nice. We can get rid of these for now. Now, let's think about, with these action and decision nodes, specific conditions and actions that I want. So let's start with actions, because actions are easier, all right, than conditions. So I'm going to say add a new item. The new item is going to be a .h file, and we're going to start with the bottom, all right? So if you look at the bottom, we're going to make these 4 actions: the patrol action, the move to line of sight action, the move to player action, and the attack action. Okay, so patrol action is first. So again, we're going to go here, and we're just going to rename. We're going to call this patrol action.h. Patrol action.h is going to be here. We're going to add it, and it's going to be an action type. So I'm going to go into action node.h. Right, here's action node.h. And we're going to use this, as a template for this. So I'm just going to grab all this, and I'm going to copy paste it in here. And it's not going to be an action node. It's going to be the patrol action. So patrol action, right? That's what it is. So I'm going to grab this and paste it in there. And it's going to include the action node, which means that I have to actually add in action node.h in here. Again, I'm just using this as a template to get going with. So this is, instead of action node, this is going to be the patrol action. Let's actually type in the right stuff, Tom. There we go, action node.h. Excellente. And patrol action is going to be here and here, right? Except patrol action won't need to do this stuff. I'm going to do this in the .cpp, which we're going to do in a second, okay? My virtual void is going to be a virtual override for the patrol action. So this is something that I'm going to do for patrol, right? And what I want to do with the actions, right, for patrol action, there's not much in here other than this for now, okay? Because remember, we're just building stuff out, and there might be a private area with some private data or something else that patrol action will do. Right now, it's not going to do anything. It's just going to be a stub for later use. One thing we do want to do is do this and copy paste into here. Okay, so that is the patrol action for the on the .h side. Let's make the CPP now, because we need that too, because we have to make a specific action for patrolling, what patrol does. And we're just going to make it talk right now. It's going to say performing patrol action. That's what we're going to make it do. So let's do that. So I'm going to say right click on add a new item, and I'm going to add in the .cpp now for this, and we're going to say patrol action.cpp. There it is. We're going to include the patrol action.h file, and we're going to use our resharp or C++ to generate definitions by declarations, where we have just these 3 things to declare, right? And our default is going to be our destructor, default constructor. And our constructor isn't going to do much other than tell us what the name of the action is, we're going to say patrol action. That's the name of our type, right, if you will. And then from patrol action perspective right here, I'm going to say that standard string, which we're going to, actually, sorry, instead of standard string, we're going to say standard cout, and we're going to say that, let's include IO stream in here, IO stream. Standard cout, we're going to say performed patrol action, or we can say performing patrol action, whatever it's going to be, because that is really what's happening, right, when we get to this part. So this is just a stub. It's just a place where we can go eventually. So this is kind of the two files we need, .h and .cpp. Okay, guys, so if you want to speed up and be with me, I'm going to make the other ones, and they're going to be identical more or less to this one. Why is that? Because I need some kind of stubs to fill in the holes of my tree. My tree needs to have leaves, and these are the leaves, and they're going to be different ones. So I need these ones to be there, and so we can copy paste those two files a bunch of times. So we're going to use this as templates. Let's make the other one. So again, if you look at what I'm making move to line of sight, move to player, attack action. Okay, so let's do the move to line of sight. Let's do all of them actually. Let's add a new item, and we'll just do them all. So we'll say do all the CPPs and .h's. So move to line of sight action .h, right? So that's the one we'll do. Move to line of sight action. Let me grab that, copy paste that to the CPP, and we'll do the same thing with. We'll just immediately add a new file, and we'll do the CPP side of the house where we want to add move to line of sight action.cpp. We'll also do another one, which is on the .h. We'll move to player action, move to player action. Let's put the action in there so we know what that is. Move to player action. And we'll say add, and we'll then immediately add the new item, which is CPP. Now you're going to say, wait a minute, Tom, you're repeating. You're right, I am. And this is the first step. Make it work is what I always say, right? And then afterwards we can refactor. So let's add a new item, and the last one will be the attack action. So attack action, okay, which will be a .h, and we'll just copy paste that part. And we'll add in the attack action CPP, new item, .cpp, attack action. All right. So we got all those stubs. They need help. They need work. Let's get those done. So let's start off with move to line of sight. I'm going to grab the patrol action that I made, copy paste all of this, and go to move to line of sight action and paste it in. We just need to change the names to protect the innocent. So we're going to say move to line of sight, action. All right, that's what we're changing here. We need to change these guards. And by the way, they do work. So we need to change all that stuff. Move to line of sight action. So move to line of sight, move, got to say the same thing, move to line of sight, action, right? Move to line of sight action is going to be a patrol action, and this part's going to be changed. And then the action is going to stay the same because that's going to be specific to the action type itself, right? So we can save that. We can go to move to line of sight action and include both the move to line of sight action as well as we know we're going to need IO stream because I'm going to print out those little funny messages over and over again. And again, now let's not do this. We just grab these things here and go into move to line of sight CPP and paste them in. And we'll just change this so it says instead of patrol action, well, maybe maybe it would have been faster if I didn't do that actually. With ReSharper C++, it just makes it faster just to do this, which is generate implementations way faster. Yeah, that's way faster. And then the only thing we need to do is make the name equal to move to line of sight action. That's the name, as well as this one is going to be default. And this one is going to be a standard string. This one we can copy paste. So we can grab this part right here from the other one and move to this one and kind of push it in there. So patrolling will perform the move to line of sight action, right, which is what this is going to be. And now we have that one done. Move to player action. Let's do that one. So I'm going to grab the same thing, control action, grab all this, right? And go into move to player action and push, kind of, put that in there. So then move to player action, right? That's pretty simple, straightforward. And replace those. This should be renamed move to player action, right? And we're going to grab that move to player action and do that. So that is replacing all those. We have an action. We also probably need to do that one there just for completeness. We can move this to change that there. And then, of course, the move to player action, we're going to make an include move to player action. And what we want to do is when we go here, we want to generate definitions by declarations with ReSharper C++, which does this. We're going to change this to default. And we're going to go make the name here. Name is equal to move to player action. And what we're going to do is we're just going to keep the last thing from the other one, this line here, so we don't have to copy it. And put it here. And I'm also going to copy this and put it here just because I don't feel like typing a thing. If I can avoid it and not make mistakes, which I'm making. Move to player. Move to player action. Okay, so there's that. And move to player action done. Last one, attack action. Let's get that one done. So we're going to grab this part right here and go back to action and put in the attack action. And you're asking me, why am I going fast? I'm going fast because there's a lot to do with this example. And I want to show you how it's built. I could have given it to you, but I figured that it's better for you to watch and see the coding so that way you have a sense of what I would do and chances are what you might do or might not do. You might decide, well, I don't feel like doing it that way. I'll do it a different way. That's fine. I mean, if you find a better way of doing it, I'm always open to seeing another structure. Attack action. So there it is, attack action. We also need IO stream. Why not? Okay, so those are those. And then we can grab the CPP stuff, which is all this, but we're going to make it with ReSharper C++ because it's just faster. Right? Because we don't have to type and copy and modify all that stuff. And so the only thing we have to change is the name, which is attack action. And this is performing the attack action, right? Which is what we're going to do here. And those are the easy ones. Performing attack action. Okay, so attack action, performing attack action. Nice, nice, nice. And those are all the actions that we want. Action. If you notice anything that has action with it, I'm going to put it inside of actions in there. So all the actions, that's this one, this one, this one, this one, this one, this one, and this one. All those ones I'm going to grab and drag and drop into there. So that's what you should have. Attack action.h.cpp, put move to line of sight action.h.cpp, control action, and move to player action. And those are all things we detailed earlier on right here. So those are all these. These nodes are done. Well, they're scripted. So why would we do this? Why would we do this instead of, making it more generic? Well, I can use these actions. Once I've coded these actions, I can have another loadout, like what we've asked you to do in assignment 4. And in that other loadout, we can reuse some of these actions for the AI to do the exact same things. Patrol, move. There's going to be something that these things mean eventually. Right now, they don't mean anything. They're just stubs. But eventually, this is where you can start. It's a good start to get going with these kind of actions. Okay, next. By the way, you can use these actions whether they are nodes or whether they are states. You can use them for state machines. You can use for behavior trees, decision trees. They're the same idea, all right? Just different implementation details. All right, so let's do conditions. Conditions take a little longer, guys. I'm so sorry. But they will take a little longer than everything else because there's more to conditions than actions. Not much more, but there is a little bit more, all right? So let's think about conditions. So the first one I want to make is the line of sight condition. So new item, I want to make, by the way, let's before we get there, let's put this up on GitHub So I will go to home. I'm going to go to changes. You can see these are the ones I've added. I'm going to say added action stubs. That's what I'm going to say, action stubs. I'm at all, home, sync, and push. And that's going to be up on our final version. So you can have all those and compare my code to your code. Action stubs. We don't need all these. In a second, we won't need them. But now what we want to do is we want to go to here and I want to add conditions. Let's add them right in here this time. So add a new item. I'm going to make the new item a .c.h. And under the .h, we're going to start with line of sight condition. So line of sight condition .h. So what do conditions look like? Well, they're the exact same as actions. Let's get the patrol action just as a stub. But conditions don't inherit from action node. They inherit from condition node. Now, do you have to make this way? No, you don't, right? You can totally make it so that it's not the same way. We can make them so they're all the same, that they're all some kind of action that you perform, whether it's an action or a condition. But to me, I find that they need to be different. So they return a Boolean, that's for sure, and this is a condition that they override. So that's something different. And instead of patrol action, this is going to be the line of sight condition. So we're going to say line of sight condition. This can also be seen as a trigger or a decision. They're called different things, and that's totally fine. So that is the line of sight condition. And where I have my line of sight condition is the class, which is a condition node, where I have this. Okay, so it looks like the action node, but there's a condition as opposed to an action. Condition returns a Boolean, action returns void. Does it have to do that? No, but one thing I also need is a setter. So one thing I need is in my condition, I want to do a couple things here. One of them is, this is where it takes longer. I want to have in my getters and setters, right? I want to be able to set the condition. So for now, it's going to be void set line of sight, where I pass in a state for the line of sight so I can modify it. Otherwise, how am I going to read the condition, right? There's different ways. One of them is to read the condition of the object that you're inside of. But right now, if we're going to make a decision tree won't know anything about what it lives inside of as a component. So that might be an issue. So the other thing is in the constructor, we want to take in a line of sight state, which is going to be equal by default to false. So I'm kind of setting it up as a default thing. So these are a little bit longer. And also, I want to keep track of it. So I'm going to say bool m underscore has line of sight. By default, there's going to be this thing as well. So this is kind of where it becomes a little bit more challenging. This is not an interface. And neither are the other ones, by the way. Patrol action is not really an interface. These are not interfaces. And neither is this or this. I just left them in there as a comment. These are actual classes, right? Because they're going to do something like the condition class. All right, so line of sight condition is not done. Let's add in a line of sight CPP this time. We're going to add in a new item, which is the line of sight CPP. So line of sight condition dot CPP. It's going to be in there. Add it, and we have to make it so that it includes the line of sight condition. All right. And now that we have this in the line of sight condition, what we're going to do is I'm going to generate definitions by declarations. I definitely want all of this, right? So finish. That's going to end up in there. And what we want now for the line of sight condition is a couple things. One, I want to set my line of sight here in my, whatever the line of sight is, I want to set it here. And I also want to name this thing the line of sight condition. All right, so that's what it's going to be, just like we did last time with the action. This will be default, so this is where it's going to be a little longer, but not much. And set line of sight, there's two parts that I want to talk about. One is m has line of sight, which is going to be the state. And I'm also going to set up the data, which is part of the node itself, to the state, because I want to store the state inside of the node itself when I'm a condition, but not when I'm an action. All right, and inside of the condition, I'm going to return m underscore has line of sight when I need to. But I don't need to. I can actually just check, right? All right, so that is my condition for line has or line of sight condition. And so that's what it does. Again, it has some issues. We're going to talk about them later. I'm going to add const here and here as well, just because it tells us to. So again, there's a few more things that are involved with making a condition compared to making a action. Why? Only because of the way I've coded it right now. In reality, actions are just as heavy as conditions. They just have different things to do. All right, let's continue. We need two more. We need a close combat condition as well as a radius condition. Let's do the radius condition next. So add a new item. We're going to call this thing the radius condition dot h. Radius condition dot h. There this is. And we're going to add that in. And I'm going to grab the line of sight condition, copy paste, right? Because it's almost like it's going to be very similar. Right? And this will be the radius condition. So radius condition. This will be detecting if the player has within radius. We don't have that functionality in the agent right now. That's for you to do. You got to do something on your own, right? So this is the stuff I'm helping with just to get going, which is what I'm hoping that you'll do. Okay, so radius condition, instead of line of sight, it'll be radius. Right? And it'll be something that makes sense because radius doesn't mean anything. It should be something like within combat radius, within combat range, or radius, within radius maybe. There we go. Within radius equal to false. Radius condition, and instead of set line of sight, we're going to set is within radius. All right, so set is within radius. All right, and condition is going to stay the same, but this is going to be m underscore is within radius, right? So something like that. Okay, so that is going to be your .h for your radius condition, just for completeness. I'm going to grab this and replace this. So it says the same thing. Radius condition done. On the .h, let's do the CPP. So right click, add a new item. Let's add a new item, which is a CPP file. We're going to call this the radius condition. Okay, it's .cp. We're going to include the radius condition.h. By the way, if it doesn't show up, you're doing something wrong, right? And what I want to do is I want to use generate, kind of declarations by definition by declarations. And I want to do the same thing. So this one will be equals to default. My other stuff here is going to be very similar to what I've done before. So what I'm going to do here is I want to set is within radius, and I want to pass in within radius. If it's within radius, I want to say the name is the radius condition. And then inside that is set within radius, I'm going to say m underscore is within radius is equal to state. So it's going to kind of take this part, and in my condition, I'm going to return m underscore is within radius, right? So that's the same kind of stuff I did before. Make these consts, right? Because that is what C# or C++ tells us. Good practice, right? And there is your radius condition done. Radius condition over. One more, and then we've done all of our node types, and then we can start coding our decision tree, which is what I want to do in the second hour. Okay, so this is kind of a lot of stuff we've done already. Let's continue. Last one, we want to do another one, new item, and .h. I want to talk about the close combat condition now. So again, okay, I'm not going to code your ranged combat condition. That's for you to do for assignment 4, but you'll get an idea of how this works so you can start thinking about it. And again, you don't have to use decision trees, but I recommend them because they're easy to work with. You'll see that in a second. So .h, there we go. And this will be the close combat condition, right? That's what it'll be called. So close combat condition will be up here. Let's do that. So close combat condition. Close combat condition means am I close enough, right? By the way, if you really want to be specific, close combat range condition. That's what it should be called, but okay, it's going to be a type of condition node. Close combat range condition is going to be this. And is within combat range, is what this should be, is within combat range, right? And the condition will be the same. This is going to be called m underscore is within combat range. That's going to be the actual data point. Did I also add the data in there for radius condition? I did not. Sorry. Because you got to figure, right? When I set the radius, then I also want to set the data to true, right? So whatever the state is. Sorry, let's go back to this. So, and because this is what I did here, my CPP, that's why I did that. So I want to keep track of the data. For now, we don't need to worry about it, but later on it's redundant. Okay, so we have this piece. The other thing is we're going to grab all this and we're going to put that in here so that we've coded everything for completeness. It looks nice is what that means. All right. And the thing within radius has to change to within combat range, which makes more sense. Combat range. Okay, then combat range, close combat condition, da 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 da. Let's make the other file. So right click, I'm going to add a new item, which is going to be called on the .cpp side, which is going to be the close combat condition .cpp, close combat condition .cpp. I'm going to include close combat condition .h. And just like we did before, I'm going to use ReSharper to, if I can do this properly, generate definitions by declarations. It's going to do it really quickly for me, and I'm going to replace this part with equals to default. All right, that's what it's going to be. And then the rest of it is going to be the same again, right? I mean, it's not going to be much different. We're just copy pasting from the same what we did. So we're going to say set is within combat range to within combat range. Thank God for code hinting. And this is the close combat range condition, right? And then close combat range set is within combat range is m underscore is within combat range is equal to state. And I'm also going to share data is state as well. And then I'm going to return this out when I need to. Okay, done. So this is your close combat range condition. Let's make these consts, because that's what ReSharper wants us to do. And it's good practice. And save all. So that is the other three type of nodes. We have now a total of 7 types of nodes. 4 that are actions, 3 that are conditions. Let's put this up on GitHub. So I'm going to go to Team Explorer. I'm going to go to changes. I'm going to go to added, we'll say action stubs. Sorry, condition stubs. Right? That's what they are. Condition stubs. Commit all, home, sync, and push. And that'll give you a good starting to get going with everything else. Okay, I'm putting it up on GitHub. Are you with me? Are you getting what I'm trying to do here? What I'm doing is I'm constructing different kinds of nodes. I'm creating different kinds of actions and conditions. They're different classes. And I'm matching it up with our diagram here. I'm saying, okay, I'm making decisions. 3 different kinds of decisions. Our line of sight decision, our radius decision, our close combat decision. And then I've made 4 types of actions: our patrol action, our move to line of sight action, our move to player action, our attack action. These are all leaf types. These are all non-leaf types, these ones up here. Okay, so that's what I've done. I've only made it one type, which is going to be a Boolean type, which the decision node is going to be of type Boolean. The action node is actually going to execute the action, whatever that action is. Okay? And there's different ways of doing this. I've coded them so that they are hard-coded, but you can also code them so that you can pass in a callback for something to trigger. It's up to you. All right, so that is this part. Let's close all these crazy things off because there's a lot of stuff here on my file. So close all just to clean all that up. And let's go back to Solution Explorer so we can see what we have. Conditions, actions done, agent is done. I've got my ship and I've got some basic things. These are like kind of core components, if you will, for everything else. And this is pretty good. We may make another filter that kind of puts in some core components. Let's put that in there. So another add new filter. We're going to call this core components because that's what these are. Action node, agent, condition node, tree node, all that stuff. I'm just going to, put it somewhere where I can hide it so I don't have to see it all the time because it's too much, right? It's too much to look at. So many different files and very hard to look at. So decision, there's actions, conditions, and agents. What we need now is a tree. And to start thinking about what a tree looks like, the tree node itself, right? We know that what the tree node is, but what is the decision tree itself? Decision trees are made up of tree nodes. So I want to make a new item. So we're in the second half. And by the way, just to track where we are in terms of the stuff we've built, we've done this part, okay? So this is done. We've done this part, okay? We've done this part. And now we're going to do these parts. And then we're getting, getting a lot done here for the foundation for what you need to do for your assignments, which is important. All right, so I want to make a new .h. And we're going to call this thing the decision tree. And this is a decision tree component, similar to a transform or a rigid body. I could put it into components, and we may do that later, all right? But for now, we're just going to put it down here so we can play with it in here and then massage it and then finally put it up on the top when we need to. So decision tree, let's add it. I'm also going to immediately add in the decision tree.cpp. This is where we're going to spend the majority of the last hour. So new item, I'm going to go to CPP and let's put in decision tree.cpp. Let's make sure that there is spelled properly and all that kind of good stuff. And it's going to include decision tree.h. Awesome. In here, we want to say that if not defined, I'm going to slow down here now. If not defined decision tree, then we're going to define decision tree. This will give you a chance to catch up as well. And div decision tree. Okay. And then what we want in here is we want a class. The class is going to be called decision tree. Now we didn't make a tree structure. We could make a superclass that's a tree structure that decision tree inherits from. And so then one day when we have a behavior tree, then behavior tree and decision tree is a tree. But for now, we're going to make it work. We're not going to make more than we need. So 2 parts, public and private. All right. Let's think about what we need for a tree. And I'm going to start with my private instance variables. Actually, we'll start with the basics. The basics are we need constructor and destructor. We need those 2 things. So we're going to make a new instance every single time. So this is going to be the decision tree. And we also need to make our decision tree destructor. All right, so those things we're going to need. I also want to keep track of my agent. So I want to refer to, even though my decision tree itself is going to be a component, sometimes what I need to do is I need to get information from the agent, right? My agent's going to give me line of sight. My agent's going to give me radius. My agent's going to give me close combat distance, a lot of stuff, right? So I'm going to keep track of my agent as a pointer. So this is the way I'm deciding to do it. You may decide to do it a different way. And decouple, there's going to be a tighter coupling between agent and decision tree in this instance. And I'm going to call this agent, right? So I'm going to keep track of agent. So my decision tree will know about my agent, or I can make a reference to it. And to help me with that, I want to be able to set and get agent. So let's make getters and setters. And I want to get agent, which is going to return an agent pointer, get agent. And I also want to set agent, which is going to return void. And I'm going to pass in an agent pointer that I can set. Okay. Again, I'm structuring my decision tree by starting off and knowing what I need, right? Next, I need some kind of list, right, of that I want. I need a list of nodes that I want to keep track of. And I'm going to keep track of a list of nodes. And notice what I said in the PowerPoint. I said I want some kind of table, an array of nodes that I can keep track of, all right? So I want to do this here privately. I want to say that I want a standard vector of type tree node pointers, which I'm going to call tree node list. Now this is for traversal only. Okay, I'm not going to use this for setting and getting anything because we're going to massage this later. And I want to talk about my conditions. I want to be able to access my conditions and my actions separately. So this is going to be the entire list, right? I may want to have all of my conditions set in one list and all of my actions set inside of another list, right? And this is just because I want convenience, not because I need them. So memory-wise, I'm not thinking about memory right now. I'm thinking about what makes my life easier, all right? So I also need some kind of ability to add a node as a convenience function. So we'll call this a convenience function that I need, which is going to be, it's going to return a tree node pointer if I want it, and it's going to be called add node. I need 3 parts to it. The tree node pointer parent, what is the parent node that I'm adding onto? The tree node pointer child, what is the child node that I'm adding into? And what about the type? So sometimes I want if it's going to the left side or if it's going to the right side. Where am I adding this node? So I need something called a tree node type, and we don't have one, but we're going to make one, which I'm going to call type. Wouldn't there be more than one agent? No, Ethan. Each tree is going to be, there's going to be an instance of a tree for every agent, right? Think about the tree as something that is your brain for the agent. Each agent or each AI is going to have its own brain, which is going to be the decision tree. Okay, so I need a tree node type, which I do not have. I'm going to add them into enums. I have a bunch of these things. Might as well. Let's add them in here too. I'm going to add a new item. I'm going to call this the tree node type. Okay. For now, tree node type is going to be under the .h. It's going to be in the source under enums. It's going to literally be if not defined tree node type, then define it. Okay. Tree node type. It's saying that it doesn't like this because it wants me to do one of these. Tree node type. That's what it wants me to do. I'm okay with that. Tree node type. Okay, cool. So tree node type is going to be an enum, right? And the enum is going to have 2 things, left and right, but it needs to be left node, and we'll say left tree node and right tree node, just so that way it doesn't clash with anything else we've done. Again, I'm not using enum classes. That would be better. but this is okay for now. Left tree node and right tree node. Do I really need these? Maybe. You know, I'm using them as, again, for convenience and labeling more than anything else. So in my decision tree now, what I want is for tree node type, which is this thing, to be added in. So I'm going to say include tree node type, right, which is this tree node type, tree node type. Did I not spell it properly? Tree node. Oh yeah. Woo, that was interesting. That's what I need there. So that is this, and it provides this. So that's what this needs for add node. So add node is going to say, I want to tell me where you're going to add it. Tell me what you're going to add. Tell me what type it is. Is it left or right? Which side is it? For now. There might be other reasons for this too later on. Okay, so that is something I need. I also want a convenience function for displaying the tree. So we want to do some testing. I want to have a display tree function. All right, that's what I want to have. The display tree function is literally going to go through and cycle through each of the nodes in the list and display it. Okay, that's what I want. And I also need a way of building the tree, which I'm going to do with privately. So it's going to be, there's a private function that's going to allow me to build the tree out, which is going to build the tree manually right now. Okay, that's what build tree does. And then finally, there's going to be some way of making a decision. For now, I'm going to make it a string out. So I'm going to make the decision. Okay, I'm going to make a decision. And sometimes I also need to be able to update my information. So for now, let's just use this as a structure. I also want to have information about my line of sight condition, my radius condition, and my close combat condition outside of my vector. They're all condition types. But for now, like I said, I'm just going to make them all separate because I just want them to work. So line of sight condition, which I'm going to call m underscore line of sight node. And you're going to say, wait, what? Why are you doing this? Yeah, bear with me. Radius. Remember, I want to make it work. Radius condition m underscore radius node. And yeah. And the last one will be the close combat condition and m underscore close combat node. Okay, so that is the .h file. It looks big, but really all it is just some convenience functions, the ability for me to make a decision, and that's it. Make decision is going to be my iteration that I'm going to use kind of an in-order traversal. So I'm going to use some kind of in-order traversal is what I want to do here from my tree. Okay? If this makes sense. Very basic, not a lot of work here yet, and it's very manual what I'm going to do, okay? Again, lots of improvements we can make later on. We have our basis. Let's do the next part, which is, let's add the CPP pieces. So I'm going to go over to decision tree, and I'm going to go to here and generate definitions by declaration. So I think this is a good spot to do it. I'm going to click finish. It's going to generate all this. I'm going to make this default, because we don't care right now about memory. And my decision tree, I got to start thinking about how to start coding all this stuff. And we want to go slow. So one thing is, we know that when we call or instantiate a new decision tree, we want to build the tree. That's the first thing we want to do. And sometimes we may want to call this build tree function again. But build tree is going to be how we're going to do everything. Let's code the easy stuff. Get agent, return m underscore agent. Okay, I'm going to return a reference to the agent. That is going to be returning const. Nice. And set agent, that's easy. M underscore agent is equal to agent. This makes agent probably going to make it const, I'm guessing. If not, it's okay. So let's set agent. M agent is equal to agent. And then add node, we're going to get back to this one. How about display tree? Well, all I want to do when we have a tree list, I want it to go through the list as an example. I don't have one yet, but I want to go through the list. I'm going to do a for each loop through the m_tree node list when I have it. And what I want is for my tree, instead of my element, think about all of my nodes in my tree node list. I want me to be able to see out the node name. I want to output that just for testing for now. And again, let's use IOStream up here. Okay. So that's display tree. That's pretty easy, right? I mean, it doesn't just loop through each of the ones that exist and display them, right? Okay, let's keep going. Slowly, we'll get there. Build tree is the big one. Make decision is going to be our, like we said, an in order traversal is what we want to do here, okay, of the tree. In order means we're going to go down the list on the left side. We're going to say, okay, so is line of sight true? No, go here. Is radius true? No, go here. And then we should get, by default, because these are all false right now, we should get an output that says patrol action. Performing patrol action is what we should get when we do a traversal. So what does that look like? And let's keep it simple for now. When we do a traversal, right? So let's do that first. Make decision will look something like this. We're going to say that we want a current node, right? I'm going to start off with the current node, which is the first node in the list. So m_tree node list 0. That is going to be the root node. We'll start at the root node. Start at root node. We haven't loaded that yet, but we're going to get there. I'm going backwards, and I'm doing this simply because I want you to see my thinking. And then I want to say that as long as the current node, right, is not a leaf, so it's not a leaf, that means it must be a condition. As long as I'm going through the condition, then let's do a single statement. We're going to say current node is equal to, if my current node left data, if it's true, then what I want is I want to go with my, and I want you to think about how this works. So I'm going to go something like this. I'm going to say, okay, so check my current node, right? Whatever my current node is, right? So if my current node's not a leaf, which way do I want to go? If it's true, right? As an example, if it's true, then my current node write data, right? If my current node write data, well, I want to do it an in order traversal, right? So what I'm saying is, let's just think about this for a second, right? Let me go back to this. I'm saying, okay, so do I have line of sight? Yes or no? Okay, if I don't have line of sight, so if I don't have line of sight, right, that's it at the current node. So if my current node is not a leaf, and I want to check to see what my current node is. If my current node data, so if my current node data is not true, so if my current node data, that is like the thing that I've set for now. You can think of this data as a placeholder for my condition, because remember, it's not a leaf, which means it's a conditional node. Then, if it's true, I want to go to the right. If it's not true, I want to go to the left. So that is going to be my new current node. I'm going to travel to the new node depending on if this condition is true or false. If it's true, question mark says, then go to the right. Otherwise, go to the left. Okay, so that's what this does. So check the current node data. Is it true? Yes, go to the right. No, go to the left. and then make that the current node and go back up here until my current node is a leaf. When it's a leaf, we know we have an action. And what I want to do then is I want to say that return my current node name, whatever the current node name is. This is not the final version of my traversal. It's a very silly traversal method, right? But it's a way of us checking from a testing perspective to see if it works. This idea. And this ternary operator is like an if-else, like we've seen before, but I've just done it in one line. You can replace data with a condition. So you can say current node get condition, but current node, because current node are all tree nodes, they don't know anything about being condition nodes. So this is a challenge we're going to have. For now, I just want to make it work. All right, so that's the one piece. I want to go to the add node next because that's the next more difficult one. And I want to switch according to type. So I'm going to say, well, okay, cool. I'm going to switch on type. And I'm going to say that case left tree node, then do something. Case right tree node. This is a convenience function, remember? We don't really need it. We can probably do without it if I want to. But I'm using it because I want to code it properly. So what I want to do is, whatever the child node is the one that I want to return. I want to return this. I want to pass this through. That's all I'm doing. I'm passing it in and then passing it through. Later on, what I'm going to do with this pass through is allow myself to do a chaining of functions where I can say my tree node and then from my tree node do something else. Okay. For now, we're not going to do that. We're going to say that we're just going to return the child node. But later on, we're going to return this, which is going to allow me to chain. Okay. So if it's the left tree node, then parent left, right, is equal to the child node. I'm setting it here. Otherwise, and I could have done this in a ternary statement as well, parent right is equal to the child node. And if I had a root type, then I can do that as well. Let's make this const. So this is just a convenience function. I don't need it really. I can probably get away with not using it and do something that looks like this more, but it's okay. Add node. All right, so now we have all the building blocks of our structure for our decision tree. Let's get into actually building the tree out manually. And I mean that, manually. First, I want to add the line of sight node or the root node. That's what I want to add first, the root node. And the first thing I want to say is m underscore line of sight node is equal to a new line of sight condition. All right, so I'm allocating memory for this. And I'm going to say that m underscore tree node list dot push back the m underscore line of sight node. So I'm pushing it back manually. Okay, this will be node 0. Okay, so this is what this does. Sets up the first node. Once I have the first node, then look, I can look at the first node and start doing the traversal. Okay, next. M underscore radius node is equal to a new radius condition. And I'm going to use add node this time, where I'm going to pass in m underscore line of sight node as the parent. And then I want to pass in m underscore radius node as the child. And let me see, and I'm going to say that left tree node is where it's going to go. And I want to say that m underscore tree node list dot push back, and I'm going to push back m underscore radius node. And this will be node 1. Okay, so what the heck did I do here? Why did I do it this way as an example? And why did I go to the left first before I went to the right? Well, I'm counting it like this. Start 0 here, 1 here, 2 here, 3 here, 4 here, 5 here, 6 here. This is how I want my list to look like. So when I print the tree out, if I want to print a tree out that looks like this, then I can literally go, okay, what if the tree was like, I don't know, 3 levels long? Then I would do 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And then I would be able to draw the tree out to make it look like this. So I can inspect what's in the tree, which is what I want to do. Okay? So that's why I'm coding it this way. So I went from 0 to 1. The next one is going to be this one, which is going to be 2. Okay, so then copy all this. And instead of m underscore radius node, I'm going to say m underscore the close combat node. And remember, these are the conditions. And then this is close combat node condition as an example. And I'm going to say that the node, the root node is going to still be my line of sight node. My radius node is going to be my right tree node, not my radius node, my close combat node. And I'm going to push onto the node list my close combat node, which is going to be node 2. One thing I realized also is when I do this, I also want to set the parent of each of the nodes when I add them in to whatever they are. We haven't done anything with the parent. I want to create that parent-child relationship. I don't really need it necessarily, but it's okay to do it. So I can create the child as an example. When I add a child in, I want the child node to know about its parent. So I can say something like child node parent is equal to parent. And what this will do is create that reference. So if I want to go traverse back up the tree, I can do this. So this is for backwards traversal. Especially if I want to do something like recursion, I want to be able to go back. Okay, otherwise I won't know what the parent is. Okay, I'm not doing recursion here. There's no recursion. All right, so this is cool. I've added the nodes in. I've added 3 nodes in, the root node and the 2 condition nodes. Let's add in the rest, which is all action nodes. So just like we did before, this time I don't care about the nodes. They can be just regular tree nodes. And I'm going to start off with patrol, because patrol is the leftmost node. Back to my picture, patrol, leftmost node. Okay, so patrol is going to be equal to add node, and I'm going to say that m underscore the radius node is going to be its parent, and I'm going to make a new anonymous patrol action, right, which is going to be the left tree node for this one. Okay, so now it asks me to include patrol action. I'm okay with that. And then what I want to do is I want to add this to the list. So I'm going to grab this node or this little line here and put it there and replace everything I need. This is going to be node 3. I want to pass in the patrol node here, right? That's what patrol node is. Let's rename this so it makes sense. Go just rename, refactor, rename. We'll call this patrol node just so that we're with everything else, but we can know it's not on something I'm saving. And I don't care about it right now. So I'm definitely going to go with the leftmost node. And the leftmost node is going to be the radius node. So the root node is going to be the radius node. It's going to be the left tree node, right? It's going to be the patrol action as an example, and it's going to be node 3. Okay. Next, let's do the next one. Again, that's why I'm using add node just as a convenience function. It's not really necessary. Otherwise, I would have more code here. It would be more messy. All right, so the next one, instead of patrol node, patron node. Patron. Let's rename this thing for a second and fix that. Sorry about that. Patrol node. Okay, instead of patrol node now, if you look at the picture, it's going to be move to line of sight action, right? So we'll just call this move to LOS node. So move to LOS node. Okay, move to LOS node. That's going to pass that in here. This is going to be node 4. It's still going to be the radius node, but the right side, right tree node. And it'll be, instead of patrol action, it'll be move to line of sight action, right? And it's going to ask me to include it. I will. And that is the next one. So that is a left and right tree node of the radius node, which means what I've done is I've added these two to this one. Okay. And let's do the last two by copy pasting those two things here and doing those ones in there. So now we're going to say that this is the left and right tree node, but instead of the radius node, we want the close combat node as the parent. So close combat node is this one. Instead of patrol node, this will be the move to player node. So this is going to be the move to player. So move to player node. That's what that's going to be. I'm going to pass this move to player node into the node list. This will be node 5 as an example, and the action is going to be to move to player action. Let's make sure we spell it properly so we can get our code hinting, which is this. Okay, so we're instantiating a new object, storing it, and we're making it, pushing it back here as an example. Yay! Awesome. Last one. This would be the attack action node, right? So this would be the attack node. Okay, attack node, and maybe make it lowercase to keep in line with everything else we've done here. So we don't care about it right now. We just want to make, we can put it in for testing. 6. There it is, node 6. You can see how that works, right? 0 to 6, there's 7 nodes, just like we said before. And then here, this would be the attack action, okay? This will go on the right tree node, and it'll be the close combat node as the parent, because that's where we are right here, close combat node, attack action, right? And I've added this all in. Nice. That is our build tree, a very manual way of doing it. But it will work. That's a beautiful thing, right? Once we've added these pieces, these I would say these components in, we have now a tree structure that we can use. We want to test it because there's issues. There's bound to be issues with this structure, right? As an example, like for example, when I make a decision, I never really update what the decision is based on the line of sight. What if I change my line of sight? I want to update that. That's where we're going to spend some time today. And then if we'll go back next day and update this structure to make it a little better. Save everything. And now, before we put this up on GitHub, I want to do a little bit of testing. So let's go to our scene. I'm going to bring up my playscene.cpp. And I want to keep track of a decision node that is like disconnected from everything else. And let's also update this to lab 7. That's the I'm GUI stuff. But what I want is in my place scene, I want this to I want to create a dummy, decision tree that's not really connected. Okay, and normally what we want to do is we want to attach this to the agent, right? So each agent will have its own tree, right? Each agent will have its own brain. But now we're not going to do that. What we're going to do for now is test the decision tree itself. So let's make a new one. We'll say that auto, we'll call this decision tree, is equal to a new decision tree. Okay, and it says, do you want to add it in? Sure, we will, because we're just testing. Hey, awesome. When I do this, it builds my tree. So let's just print out what it built. So I'm going to say decision tree dot display tree. And you know what? Maybe decision tree dot display tree, too wordy. Let's rename this thing. So refactor, rename, and let's call this display. We'll just call it display because that makes more sense. And it reads better. Decision tree display. Display the decision tree. Right now, it's not going to do much. It's going to display it in order. We can be fancy and make it display like a tree if you want to. Later. All right, and let's just run it. Let's see what happens if I did this. Is it going to cause a problem? What's going to happen? Oh, well, one thing we need to do is also, we can't display the tree. Let's also associate the agent. Decision tree. And we want to set agent to m_p ship. It's got to be of type agent or else it won't set. So that gives us a reference to the agent, which is this. Okay. In real life, if I was going to add this decision tree to the ship or to multiple ships, I would add it as a component and would pass in a reference to this, right? The ship itself in here. Okay. All right, but we're not doing it. We're just going to try it out like this and see what happens. So let's run it and see if it breaks. Okay, and there's my thing. It says line of sight condition, followed by radius condition, followed by close combat radius range condition, right? That means when I look at the diagram, it's done this, this, and this. That's good. And then it does my patrol action, my move to line of sight action, and then it did my move to player action, and finally my attack action. So it actually loop through each of the issues, and we know that all of those things are good to go. Otherwise, we would have had an error. So we've allocated memory, and we've created our tree structure. This is a great spot to put it up on GitHub. By the way, this is one little picture you can take for your lab 7, right? Because this is proving that we've got some structure for our tree right here. Okay. And let's put this up on GitHub. So we're going to go to Team Explorer. We're going to go to Home. We're going to go to Changes. And I'm going to put in created decision tree first draft. Okay, commit all. And then Home, Sync, and Push. So very, very simple. You know, just trying to we made it manually. We didn't traverse anything. We're just basics, right? Okay, so now that we have this, what next? What do we do next? We're almost done for today. What I want to do is make a decision, right? So let's go back to decision tree.h. We can make a decision, but we need to poke around and get some stuff changed. So before we make a decision, we want to set the condition for my so my line of sight node, as an example. I want to poke around and make a change the line of sight condition, right? My line of sight node condition. I want to set it, the actual node itself. I want to set it to if I have line of sight. So it's going to be whatever the line of sight condition is. I want to, when I call make a decision, whatever the line of sight decision, or if I have a line of sight, it's going to set it. Right now, I don't have line of sight. So when I make a decision, it's going to be all false. And what I should get, if I just call make decision right now, everything should be false. And I should return the name patrols, which is what we should be doing. The patrol name should come up. So what I mean by that is, if I go back to my scene, and if I make a decision, so display it, and then afterwards, let's just do something that looks like this, just for testing again. So we'll do a separator, so we know what this is. And what we want is standard cout of my decision tree. And I want to make decision. Make decision is actually going to return a string. That's going to tell me the type of decision that's being made by the name, because right now all it does is it's going to return the name of my decision. That's what it's going to make, the name of my decision, the name of the node that is being passed back out. Okay. Now we know that the current nodes are the way they are, but we don't have any reference or context in this traversal. So we don't have a context. We're not like going through, and I don't know what type it is. I haven't done any of that work yet. That's for next week. So we have to do some improvements after this, right? All right, so cool. Let's run it and see what I get. If I just do some making decisions, then I get control action. That makes sense, right? Because by default, everything is false, right? So it did exactly what I thought it was going to do. So again, if I go back to play scene, let's just add another little one of these just to make it so that we can see it. Here's my patrol action, and we'll even add an extra /n just to give us some separation away from the regular debugging. Again, if I run this thing, what's happening? Why am I getting that here, right? Patrol action. Well, the reason why I'm getting the patrol action is because, let's think about this, right? Everything starts off when I look at my decision tree itself. So if I go to Solution Explorer, And if I look at just basic core components, let's look at my tree node.h. Everything is set to defaults. Look, my data is false. And because my data is false and I haven't changed my data, then it's going to go to the left. Okay, let's force it to go to the right. So I'm going to say I got line of sight, okay, but everything else is false. Well, if that's true, if I had line of sight, it went to the right, but everything else is false, then I should have move to player. Let's try that and see if that works, the decision. Again, small baby steps, guys, for testing. So what I want then is in my decision tree, I want to change my, when I make a decision, this part here, I want to make it so that, let's go to definition. I want to say that by default, I want to set my tree node, my current node, I'm going to say that current node dot data is equal to true, setting it directly, okay? And if I say it's true, then it goes through. If current node is data is true, it's going to go to the right node, but then it's going to fail on the second pass because I'm only going to change it once. So if I do this, and if I press play, I should get move to player. Traverse the tree. Nice and nice, right? That's what I'm trying to do. That's what I'm looking for, guys. I'm trying to make it so it's literally, is it true or is it false? Is it a yes or is it a no? If it's a yes, it goes to the right. If it's a no, it goes to the left, okay? And we have a lot of extra work here that we can trim later on. All right, so cool. That's nice. But I want to get this information from the agent. So whatever the agent's line of sight is, I'm going to say that, hey, get agent, and I want to get their line of sight, right? That agent line of sight, get agent line of sight. What does that return, right? And I want to set this as agent line of sight to whatever the data is for my main current node. So current node, I want to say that dot data is equal to current node data is equal to get agent has line of sight. I want to pass in whatever the agent has for line of sight, and I'm going to pass it into this. We may have some issues here. Let's see why. And we'll code this in and see what happens. So, and then we might stop here for now. Let's run it and see what happens. And tell me if we do get a problem, why we get this problem. So why are we getting this problem, guys? Here it says read access violation was null pointer what? Why am I getting a null pointer? So look at this. This is the call step. So I'm going here, then my place scene, I start, I'm making a decision. The decision totally works. But then when I go and access the agent's as line of sight, I get something that's messed. Well, a couple things happen, right? I mean, I set the agent with this, I set the agent, right? The agent itself, this is my agent itself, right? And I want to, as line of sight is something that's being returned out, okay? And I'm storing it nicely, right? Nice, because, I mean, okay, let's do one more thing before we go here. And let's go back to my decision tree.h or .cpp, and let's see what my problem is. Let's comment this out, and let's puzzle this part out, because now we got lots of levels of abstraction, which is causing part of our issue. All right, so first of all, does my scene work the way it is with my agent? So if I move this, and can I still get line of sight? That's important. All right, so does everything else still work? If that doesn't work, then something else is broken. Let's do that. So we'll move my ship position up here, and then we'll move my target position up there as well. Okay, so that it records line of sight. Look, that's okay, because it's passing through and it's recording line of sight. Nice. Okay. But when I want to, my data, I make a decision, as an example, and I do it. Let's take a look at my placing and the way I've set it up. My placing, I'm doing my decision tree way up here, and my ship is being called down here. which means it's not even in existence yet, right? So that's why this fails, my friends. If I try to do the ship, because the ship hasn't existed yet, if I pass this stuff, this piece, if I take this piece here and I pass it towards the bottom of my ship for testing, down in here, the bottom of my start method, this is different. Now this should work. Let's see what happens. So if I go back to my decision tree.cpp and I turn it back on again, and I say that, hey, let's get the line of sight. It's still going to be patrol action, because right now by default has line of sight is false, right? Let's run this thing and check it out again. It should not fail. Okay, it should not crap out like it did before. Still gives us patrol action because by default it starts off as no line of sight. Cool, line of sight. Okay, but we don't want to do this. We want to make it so that I have an update function that I call. So let's, in my decision tree, I want to be able to call my decision tree update whenever I want to update my conditions. So I want to say something like, let's make a void update function. I'll put it here. And my update function, it's going to do the following. It's going to say that I want to change my m underscore line of sight node. I want to change the set line of sight, right? My state when it comes to set line of sight. I want to set it to my agent. And I want to get line of sight from the agent. So has line of sight. Remember, the agent has line of sight. This is why I made the agent in the first place, in order for me to say, hey, agent, whoever you are, right? I don't know what the agent is, but whoever the agent is, I want to take their line of sight and set it to my line of sight here. Okay, that's what I want. So that's what I want. I don't want this, which means that instead of doing this, every time I make a decision, if I'm called to make a decision, first I want to call update. I want to call update when I'm making a decision. Making a decision doesn't always happen. Maybe it only happens every once in a while or whatever. And I'm not going to definitely call this every update. It's only going to be called when I need to make a decision. I update my my information, because decisions can't be made every frame. If you make decisions every frame, you're going to have a very jittery bot that runs around. Okay. So update is cool. All right, cool. And let's see if this works the way it is right now. I got some other questions here. Could you make it where the line of sight node only updates if the nest node in the list, the way you don't update every node? Yes, I could. The next node in the list. Yes, I could. But again, let's just one thing at a time. Yes, you've got the right idea. All right. All right. So let's try this out and see what we've got, and then we're going to stop for today. So it says patrol action again because we've got no line of sight. Okay, so this is what I want to do now. I want to enable, when I move my object around, I want to call in the placing, I want to call my decision tree again, right? In order for me to, I got my agent here, but I want to make decision somewhere in my UI function. The only way that I can do that is if I set up inside of my placing.h. So here's my placing. It's the last thing we're going to do, guys, and then we're done for today. In my placing.h, right, I want to, when I move, I want to make a decision, right? And I want to move between move to player, have line of sight, and move to patrol if I can't see the player. That's all I want to do right now. Okay, so very simple. So inside of my placing.h, what I want to do is I want to go here and I want to say something like my decision tree pointer, right? And I want to call this what this is called, just so that way we don't have a lot of clashing. So this, and I want to include this, which means I don't have to include that inside my scene way up here, which is where I've added it right now. Okay, and then what I want to do is further down, and here I don't want to make this auto. It's already been declared. I want to create it once, make a decision, and then when I move, every single time I move, make another decision. So take this make decision piece out. When I move my ship, I want to make a decision. Let's see if this works. So I move my ship's position every time I want to make a new decision. All right, let's see if that works. Okay. Or if it crashes and breaks and burns. All right, let's see what happens. So remember, what I want is I want to see line of sight changing. I want to see line of sight changing. I want to see the decision changing based on line of sight. Okay, let's see what the issue is. It says I've got a decision tree. It says expected this. All right, nice if I put in a semicolon. Semicolon, like that. And let's try that again. Syntax errors. And last thing, guys, then we're going to be good for the day. Okay, cool. So we're good. Patrol action. If I move my ship, let's bring up I am GUI. It'll show this a bunch of times until I have line of sight. Let's try this. So ship position, we're going to move this up. We still have patrol action because nothing's happening. But as soon as I bring my target into place, right, it says that I have line of sight, but you know what? I need to move this around for me to do it because I don't have another mechanism of this. So this is good. And I want to move this to this. And you can see it immediately changed to player action. So it did it, right? And then if I move this down into some place where it doesn't have line of sight, example, if I take my ship on the y-axis and move it away, now it's patrol actioning, no line of sight. A decision tree can change its action based on what it's going to be doing, right? Now, this is a very simple example of switching and calling the decision based on if I have line of sight or not. But guys, this is a great place for you guys to start because the decision tree right now is global. But what I really want to do is attach this as a component to each of my agents. And we're going to do that next week. This week, we're done. From a screenshot perspective, let's take a few screenshots. You can make it more glamorized if you want to. I definitely want a couple of screenshots of some of the things we've done. One of them definitely would be inside of the command prompt. So we want to run this in the command prompt. Please take a screenshot of this to show me that you've got this played out here with a patrol action by default. Make another one, another screenshot. If I bring up my I am GUI as an example, I'd want to see that you can move your ship. If I move it up here, and then I move this target up here, maybe just move it around again, right? We should be able to see that this changes from patrol action to move to player action. This is also a nice little screenshot to show that, okay? And I know it's simple, but it proves that your code is working. And then maybe one more screenshot of your this stuff, this structure that I've made you do, right? Which shows this. Show me this, that you've done this part. And if you've got all that and you've worked on it together, awesome. You've done the first bit of what we need for the next week. So now going back to this, let's put this up on GitHub first, and we're done for the day. So home, changes, I'm going to say, kind of tested decision tree. Tested decision tree. First draft. All right, so first draft of tests as well. Home, and then sync and push. So that kind of tests everything out. Very basics of making a decision tree and all that kind of stuff. And we're not even using the functions properly, but that's okay. We'll improve this next week. All right, great. And what about where we are on the lab? Well, we've kind of done it all. We've made a tree structure, right? And then we built a table of array of nodes. We added a add node function, right? As well as we needed to add a root node first. We did that. And we've done a lot of other stuff too. So we've done all of this stuff, kind of everything that we've kind of said we're going to do this time around, we've accomplished. So this is a great start for you guys in terms of the stuff that you guys have started with. So that way you can make your assignment 3 and 4 work. In fact, this is way more than you need for assignment 3 because the assignment 3 needs you to move around. And please take a look at the details around both assignment 3 and 4 to make sure what you need. And this is using decision trees. But like I said, one last thought before you guys go. You can use whatever decision structure you want. If you want to make a decision structure that uses state machines, I'm okay with state machines. If you want to use decisions, you can make decisions. If you want to make behaviors, you can do behaviors. Whatever makes sense for you, for your game, right? So the state machines are okay too. But some of the challenges are, how are you going to accomplish the things we've asked you if you don't use a tree structure? How are you going to get full marks? That is the challenge. Because if you look at your assignment instructions for assignment 3, and really quickly here, right, it says for decision making, right, you need a node class. So I've given you that already. You need some kind of collection of node pointers to enable iteration across all nodes. All right. Okay, some kind of STL vector list or structure. We've done that. I've given you this, right? You need some kind of appropriate actor sprite. That is something on you. This not the spaceship that I've made. That spaceship is really not an actor, but an agent, an enemy. That's the enemy class that I've given you, right? And some kind of interesting map. You're placing as simple sound effects. And if you look down, there's some debug views and debug keys. You can use I am GUI if you like, right? Or something else. And some kind of player animations, that's on you. Player combat capabilities when it comes to close, when you're in range combat. And health bar, obstacles, and the base enemy setup. Nowhere here in assignment 3 does it tell you need any kind of behavior, really. It's just a setup for everything else you're going to do in assignment 4. But one thing that it does say is this, node class. Now you can use a node class with state machines. That's totally fine. It's just that each node is a decision node or a state node as opposed to a tree node. Okay, same kind of idea. And in assignment 4, really quickly before we go, now you get to see some of the stuff that I've asked you. Look, here's some AI actions. The patrol action. I've given you this, but it's in stub format. It doesn't actually do the patrol action. The move to player action, right? It's in stub format, right? The move behind cover, it does not exist. Wait behind cover, does not exist. These are the things you have to do. You have to make some of these, right? And it's a game, so it's going to have other actions. Close combat attack, a flee, a move to line of sight, move to range. These are all the actions, as well as all the conditions that you have to test in your tree. I haven't mentioned all these. These are just the actions that your AI will make based on the conditions that you set up. I highly recommend you draw it out. Start thinking about making a tree structure like this when you do your assignment. Or if you're going to use behavior trees, something that looks like this. Or next week when we talk about state machines, draw the state machine out. All these things are important because if you don't plan, again, like I said earlier in the lecture today, it's like spraying and praying. We don't want that to happen. All right. Any questions before we go for the day and for the week? I know there's a lot we covered here, guys, and it's a lot to absorb. Please, if you haven't had a chance to, please go through the video in its entirety and make sure you understand how to do all this stuff, because it will help you understand how to do basic decision making. Okay, very simple. Okay, if there's no more questions, I'm going to stop recording, and I'll see you guys next week.